Algebra 2! Hope you guys are having an awesome day. I know I am, because I'm making an algebra video. What? Okay. Anyways, we are moving on to chapter 6, which is multiple. Okay, 6.1 is multiple representations of functions. We're going to end up doing a lot more. It's just like more with functions in general. Okay, so today we're just going to be looking at different representations of functions. So we'll be able to like go from one thing to another, words to functions, functions to tables, tables to graphs, graphs to words, and then be able to understand visually and conceptually what each representation I can talk tells us. Okay, so there's lots of different ways we can represent functions, one of which is words. We also have function notation. We also have tables. We also have graphs. And so you can basically take any scenario and represent it in any way. Okay, so for example, right, this is kind of spring break-ish time, and so probably many of you have traveled. When you're gone, you have to kind of deal with, if you travel outside of the United States, you have to deal with currency exchange. And so that might be a scenario that you'd have to use a function for. So let's say we're traveling to, I don't know, let's go to Costa Rica, because I was there last summer, and so, yeah. Okay, so traveling to Costa Rica, you need to be sure you get exact exchange rate for your dollar. So in this scenario, one US dollar is 520 and 30 cents colones. And 3/10 of a colones. Okay, so function notation, we could take that same scenario and represent it as a function. And if we let U, for example, be US dollars, or let's use D, I don't like U. Let's use D as the dollar and C as colon. So if it's a word problem and we're translating it to functions, we have to make sure that we like define our variables, because otherwise you're going to get confused and you're not going to know what's coming. And at the end, it's hard to go back and figure out what's what. So anyways, we want to make sure we define our variables. Anyways, so I let D equal the number of dollars, C is the number of colones, and then we could write C as a function of D, or we could write D as a function of C. So I could have the number of dollars equals blank number of colones, or I could have colones equals blank number of dollars. And since I have one US dollar is 520 colones, I'm going to go with the latter of the two. So I'm going to say something like colones, the number of colones is equal to 520 30 times the number of dollars, right? Because if I have $1, that's going to be 1 times 520, and that's the number of colones. If I have $2, that's 2 times 520, that's the number of colones, okay? Now, you also might, not in this case, but maybe there's, for every time you take money out, maybe there's a fee, maybe $10 or something like that. So then, you would subtract whatever amount that you need in order to keep the function real. But that's not our scenario right now, so I'm going to leave it as C equals 520.30 times D. You could also represent this in a table and have your list of dollars and then your list of colones, something like this as your table. And then you could also graph this. This is a linear function with a y-axis of colones and an x-axis of dollars, and y-intercept is 0, slope is 520.3. So you could even graph this. And in this case, it doesn't really make sense to have negative in there. I mean, I guess you could go in debt while you're traveling, but for the most part, we're going to talk about $1 being 320 colones. And so therefore we will have a linear relationship, and it's really just going to be on the positive in the first quadrant, and okay, cool. So you kind of see overall how you have, 4 different representations of the same thing. And basically, like, by the end of today, I should be able to give you a graph and you tell me a story about it. You should be able to do that. Maybe it'll just be random and you come up with something really funky, but that's okay. Be creative. All right, so there's a lot of ways to like interchange between the two functions, or between the 4 different representations. And this little table just gives you a couple places to start if you're not really sure what to do. So like if you start with a table, then maybe you want to look at the differences between the y values and see if there's a linear relationship or an exponential relationship. Maybe you want to graph the points and see what happens. Maybe if you can't quite get an equation yet. If you start with a graph, then maybe you want to kind of see, oh, what is the parent function? Is it an exponential parent function? Is it a log parent function? Is it a linear parent function? Is it a parabolic linear parent function? So that kind of gives you like the type of relationship that it is. You could also make a table from a graph, pick a few points, lots of different options. You could perhaps get an equation from it. Same thing, if you start with an equation, you might want to like make a table if you want to go to a graph from an equation. All sorts of different options. And then a verbal description, that's probably the hardest one for people because you don't do it that often. But basically, you have a story and you want to translate that story to math. And so that's going to be kind of what we look at for the rest of today. Now for these graphs, there might be more than one correct answer depending on how you argue it. So make sure if you think you are right and it's not the same thing that I have, make sure you argue it and say, justify it, right? So you might be given graphs, which we are. We're given 4 different graphs and we're given 4 different situations. And it says, okay, match each situation to its corresponding graph. Sketch possible graphs if the situation doesn't match one of the graphs provided. Okay, so number 1, due to a recall, a company's profit drops sharply into a loss but rebounds a few weeks later. And you want to look at the graphs and see, is there something that, drops sharply and then slowly recovers? And I think probably the best one for that would be graph D, because here's, okay, here's our profits, and then, oh my God, a recall, and we lose a lot of money, and then like we slowly regain our money back. Okay, so D is probably the best answer for number 1. 2, value of a car declines as the car gets older. There's only one graph that has a steady decline, and so I would say graph C is probably the best option for that because your car depreciates over time. It's worth less and less money, and it's kind of an exponential decay type of deal. So that, I think, C is probably the best answer there. Souvenir shop. Sales are seasonal. High sales in the summer and low sales in the winter, which kind of makes sense. So then you want to find a graph that kind of like goes up and down and up and down and up and down and up and down and up and down, right? And probably B would be the best scenario for that, right? Because you see a steady incline and then, oh, that must be the summer months, and then that must be the winter months and summer months again, and then back to winter. So I think B is the best scenario for 3. Now 4, depending on what you graph, might look differently, but you have an airplane ascending to a height of 30,000 feet, then descends to a cruising altitude of 24,000 feet. Now if you're graphing its height, I don't think any of the graphs match this description, because if you were to actually like graph this, it's ascending, so it starts at 0 feet, right? And then it increases up to 30,000, and then it like goes back down to 24,000 and then like levels off, right? And so that's probably a better scenario than any of the graphs that they give you. And it does say that you can sketch a possible graph if you don't like any of the ones that they provided. So I think that's probably something, I think that graph kind of makes sense. Okay, next we've got kind of a word problem. We're starting out with words, and then we want to create a table, equation, and graph. So we have part-time students at a university. They have to pay an enrollment fee of $179.35. Okay, so that's like your fixed rate. They have to pay that no matter what. Then they also pay $218.40 per every credit hour that they take. Okay, so 1 credit hour is $218. 2 credit hours, $436. Okay, so we're going to create a table, an equation, and a graph that represents this scenario. So you might want to start with the graph, then find the table, then the equation. Or maybe you want to find the equation first, then make the table, then the graph. Or maybe start with the table, then make the equation, and then make the graph. It doesn't matter what order, whatever makes sense to your brain. For me, I'm very algebraic, and so I want the equation first, and then I can make the table with that. So I'm going to do my equation first because I can tell already that this is a linear relationship. So I know that my total cost is going to be $179.35 plus $218 per credit hour. And so if I have X be my credit hours, number of credit hours, then I can say, okay, my total cost is going to be $179.35 plus $218.40 times the number of credit hours that I sign up for, so times X. Take a minute to notice what I did, okay? I have my equation, C equals 179, blah, 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 with X, right? But I also state the context. I say C is the total cost of enrollment and X is the number of credit hours. So even without the original problem, I still know what I'm talking about and I still know what the variables represent. So this is really, really, really important if we're talking about real life situations. You really have to define everything in context. Okay, so from there we can just make a table, X versus C, and then we can make a graph, X versus C. X is going to be my independent axis, my x-axis, and then C is going to be my y-axis. Okay, so for my table, notice I picked 0 credit hours, 1 credit hour, 2, 3, 6, 9, 12, and 15 credit hours. Why such weird numbers? Well, 0 is, taking no classes. But generally, a typical class in college is about 3 credits. So it would generally go up, right? 12 hours is generally a full-time student. 15 is over full-time or kind of average-ish. 18 is definitely over that, but nobody really takes more than 18-ish credits. So anyways, it depends on the situation, but I just picked those values, and then I can just plug those into my equation to figure out what my cost is going to be. So I'll go ahead and do that, and you can see how cost of college can get up there. All right, so that's my table. Then I can graph all of those. I mean, literally just graph it. This is a linear relationship. Slope is going to be 218, y-intercept, right? So this is my slope, y equals mx plus b. That's my slope, that's my y-intercept, so I can just graph that. Or if you don't recognize that those are the slope and y-intercepts, you can now plot the table. And you have a graph like that. Please use graph paper for yours. I don't have graph paper on this thing, so but make it nice and make the scale nice and but anticipate. Don't make a graph that's takes up your entire page. I've seen people who make their graph so big and then they realize they need it even bigger, and so then they make it really big and it's covering other things. Oh my god, please don't do that. Just anticipate, and if you have to, you can start over. Not a big deal. Last example, I would say you try it first, and then I'm going to give you, in about 5 seconds, I'm going to give you the answer, so pause it, and then I'll just give you the answers and just check and make sure that yours work. Okay, and there's your solution to that last equation. Make sure you read very carefully, because a very common mistake is people to start at 0 for something like this and make a positive sloping graph. Sorry, you didn't really see that. Bam, a positive sloping graph, just because they just assume that distance is going to increase, but he's actually dropping from a cliff down to the ground.